Welcome back to Power Series. I'm Kevin Tokoph on Catalyst University. Make sure to like this video and subscribe to the channel for future videos and notifications. In this video, we have a power series, a series from n equals 1 to infinity of negative 1 to the n times n divided by 4 to the n, and then times x plus 3 quantity to the n power. And we're asked to determine the interval of convergence for this power series. Alright, so we haven't actually done a theoretical video on power series interval of convergence because the best way to really do this is to dive into a problem. But I'm going to go through some of these steps and factoids about interval of convergence for power series as we go along in this first video, and then the next two examples in the next videos we'll just straight up do the problem. Now, to preface this, when you have an interval of convergence problem for a power series, generally speaking, the first thing you're going to want to do is either do the root test or the ratio test on the power series. Now really, you can use any series convergence test to find L, the limit, but it tends to be easiest with the ratio test or the root test, and between these two, generally the ratio test ends up being more common, but you just have to look at the particular series. And once we find the limit, L, we're just going to set L less than 1. In fact, that's the second step. We're going to set that limit L to being less than 1, and that's going to allow us to find endpoints of convergence. So it turns out that, remember with power series we have both n and x, but we're really concerned about this x. So it turns out that for only some given values of x, so a range or an interval, only within that interval of x values will the power series converge. So I'm going to jump ahead a little bit. We haven't worked the problem, but it turns out this power series converges when x is between -7 and 1. So when we set the limit less than 1, it's going to allow us to find the endpoints. Our endpoints are 1 and -7. So between these two endpoints, all the values of x cause this power series to converge. There still remains one question though. We know between these endpoints the power series converges, but what about exactly on the endpoints? Exactly on x equals 1 and exactly on x equals -7? Well, the third step is actually to check the endpoints, which we'll actually do on the next slide. So now let's go and work the first two steps of this problem. We're going to use a series convergence test on this power series to determine L, and then we're going to set L less than 1 to find the endpoints. So this power series, it looks best to probably use the ratio test. So we're going to use the ratio test. That's probably a good bet. So remember what the ratio test says is the limit L is equal to, the limit is n goes to infinity, and remember we have in the numerator we have all of our n plus 1 terms, and then we divide by the regular n terms. Alright, so over here we have -1 to the n plus 1 times the quantity n plus 1. Then we have the quantity x plus 3 to the n plus 1 power divided by 4 to the n plus 1 power. And then we essentially just multiply it by the reciprocal of this argument of the power series. So times 4 to the n divided by -1 to the n times the quantity x plus 3 to the n power. And pretty much from here we're just going to do algebraic simplification. Alright, let's say -1 to the n plus 1 power is the same as -1 to the n times -1. Now this n plus 1, we can't really do anything with that, so we'll leave it. But this x plus 3 to the n plus 1 power can be written as x plus 3 to the n times x plus 3, which is to the first power, but we'll just leave that off for the moment. And in the denominator here, 4 to the n plus 1 is the same as 4 to the n times 4, or 4 to the first, so we have that. So now, over here, we've simplified all of the n plus 1 terms that we can. Let's cancel a bunch of stuff. Well, notice the -1 to the n cancels because there's one on the numerator and denominator. 4 to the n will cancel. X plus 3 quantity to the n will cancel. And so pretty much what we're left with is over here, the limit as n goes to infinity of -1 times the quantity n plus 1 times the quantity x plus 3 divided by 4. And then over here we would have technically a 1 over n, so 1 over n. But let's go ahead and put the n over with the 4, so we can put just one big term here. So this is the limit as n goes to infinity of -n plus 1 times x plus 3 over 4n. Alright, so what we can actually do, because this limit is only in terms of n, if we have any term that's not in terms of n, and normally it's going to be either a constant number or in terms of x, like this x plus 3, we can actually pull those outside of the limit. And notice the only real terms we have here where we can do that are this x plus 3. So the x plus 3 we can actually pull outside of the limit, which is what I've done on the next row here. So the limit L is equal to, and remember, since the ratio test has the absolute value signs, when we pull the x plus 3 out, we have the absolute value of the quantity x plus 3, and now times the limit as n goes to infinity of negative quantity n plus 1 over 4n. Now, essentially, we can drop the absolute value signs, but when we do, that causes this negative sign to disappear. So the limit is really equal to the absolute value of x plus 3 times the limit as n goes to infinity of 1/4 times n plus 1 over n. All right, so we're making some progress here. The limit L is really the absolute value of x plus 3 times 1/4. And notice, we've already evaluated this limit, and we can really evaluate this in multiple ways. We can recognize that both powers of n are the same, so it's just the coefficient of the first n divided by the coefficient of the second, so 1 over 1. You could use L'Hopital's rule, but the whole point is this n component is 1. So that's why it goes away, and we have the limit is the absolute value of x plus 3 times 1/4, which I'm going to rearrange and do 1/4 times the absolute value of x plus 3. Really doesn't matter. But this limit, what we just found, we're going to set less than 1. Alright, so the first big step is over. Now, this absolute value, particularly the x term, the x plus 3 here, is really, really important. And you'll see why it is now that we're setting the limit less than 1. So we have 1/4 times the absolute value of x plus 3 is less than 1. Alright, let's actually just go ahead and multiply this 1/4 by 4 on both sides. So 4 moves over here, so now we have the absolute value of x plus 3 is less than 4. Alright, now we can evaluate this, but we have to do it twofold because we've got absolute value here. Here's what we do. So in one case, we drop the absolute value sign and just have simple x plus 3 is less than 4. Alright? But in the other case, what we have to do is we still have the x plus 3, but we flip the direction of this sign and do greater than, and then do the negative of the number over here on the right side. So instead of being x plus 3 is less than 4, we have x plus 3 is greater than negative 4. And this is something you're going to have to remember, kind of dig up some old algebra skills from a long time ago. But we have to do both of these and compute them separately. So this top one, x plus 3 is less than 4. Subtract 3 from both sides, pretty easy. X is less than 1. And then over here, x plus 3 is greater than minus 4, subtract 3 from both sides, and we get x is greater than negative 7. And if we put these two things together into one combined inequality, we basically have that the interval of convergence, or at least a rough estimate of it without endpoints confirmed, are x is between negative 7 and positive 1. Alright, so what we've done so far is we've used one of the series convergence tests, i.e. the ratio test, to find L. Then we set L less than 1 and we find our endpoints. Alright? Now, before we go any further, one thing I just want to remind you that's very important when you're actually doing the ratio or root test, which is generally what you're going to do, is remember when you pull the x component out of the limit, it's very important to keep those absolute value signs, which you can now see down here where we actually determine what the endpoints are. Now, what do we have so far? We have two endpoints, and we know that between these two endpoints, so for values like negative 6, negative 5, 0, whatever, any number between these, any value of x between those will cause this power series to converge. If we look at a number outside of this range, like positive 2 or negative 8, and plug that in for x, that would cause this entire power series to diverge. But again, the question remains, do the endpoints exactly on those, 1 and negative 7, cause this power series to converge? So what we have to do is check the endpoints. That's what we're going to do on the next slide. And ultimately what we're going to do is do two different cases. In one case, we're going to plug the 1 in for x and evaluate the power series. And then in the other case, we're going to plug negative 7 in for x and evaluate the power series. So we've still got quite a few more steps, but again, if you just follow these, it's not that bad. Alright, so our first case. Let's look at plugging in for x. Let's plug in positive 1. That was one of our endpoints. Let's plug in positive 1. So we plug in positive 1 for x, remember. We get that the series from n equals 1 to infinity, we have a negative 1 to the n times n over 4 to the n. But if we plug in a 1 here, 1 plus 3 is 4 to the n power. Now, a lot of times these interval of convergence problems for power series are designed to work out very nicely. Notice the 4 to the n's cancel. And so all that you're left with is the series from n equals 1 to infinity of negative 1 to the n times n. Now, let's just plug in a few values of n. So, for example, 1, so this is going to be 1 times negative 1, so the first term is going to be negative 1. If we plug in 2, n is going to be 2, but this negative 1 squared will be positive 1, so the second term will be positive 2. And what will happen is, if you keep looking at terms, it'll be negative 1 plus 2 minus 3 plus 4 minus 5 plus 6. And so you basically have the partial sums alternating between positive and negative, so to speak. And so when you have a case like that, remember that's where you have no sum, because the partial sums keep oscillating between positive and negative. They never settle on a single value. Therefore, this first case where we plug in x equals 1, that does not exist, because if we take the limit as n goes to infinity of negative 1 to the n times n, again, it's just going to alternate. It will never settle on a single value, so it does not exist, or diverges. And if the endpoint diverges, then that endpoint is excluded from the interval of convergence. So what that means is, if we were to use the value 1 in here, the power series would not converge, it would diverge. So 1 cannot be included in our final answer. Okay? Now let's check the other endpoint, which is negative 7. So we're going to do the same thing. We have plugging negative 7 in here for x, and that's going to give us series from n equals 1 to infinity of negative 1 to the n power times n divided by 4 to the n. And when we plug in negative 7 in here for x, negative 7 plus 3 is negative 4 to the n power. All right, let's do a little bit of algebraic simplification here. All right, so this negative 4 to the n power, let's focus on this. If we think about breaking this up as negative 1 times 4, quantity to the n power, then we can see that we have a separate negative 1 to the n power times positive 4 to the n power, right? And so what will happen is, you can see the 4 to the n's will cancel, and all we'll be left with is the series from n equals 1 to infinity of negative 1 to the n times negative 1 to the n. And if you combine these two alternating terms, the series no longer alternates, because what you get is negative 1 to the 2n power times n. Because remember, exponent rules allow you to add the exponents as long as the bases are the same, and they are, both negative 1. Negative 1 to the 2n power is never negative, it's always positive for all values of n. Because if you plug in 1, you get negative 1 squared. If you plug in 2, you get negative 1 to the 4th power. So this is just 1. So the series is really just this simple, n equals 1 to infinity of n. And this obviously diverges, it goes to infinity. So negative 7, if you plugged it in for this power series, would cause it to diverge. So that means neither of these two endpoints are actually part of the interval of convergence. It's only values between negative 7 and positive 1, but not including those values. So actually, in the way we wrote our initial inequality, if we were writing the interval this way, ironically, it was actually correct in the way that it was written. If one of our endpoints actually converged, let's say it converged at 1, we'd have a little line under this, so it would say x is less than or equal to 1. But we don't have that, okay? And when we write it in this notation, the parentheses basically tell us that neither of these endpoints are included in the interval of convergence. All right? So hopefully this video gave you some understanding and intuition behind how you determine the interval of the convergence for a power series. And we're actually going to do 2 more examples of this, so join us in those videos. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.